To start off, we're going to look at the first hill, and we're going to find the vertical displacement of the ride climbing that first hill is 39.02 meters. Then we're going to see that the work put in by the motor using law of conservation of energy is 1.22 megajoules, and the power required for this is 28.42 kilowatts. At the top of this hill, the roller coaster will have a gravitational potential energy of 1.39 megajoules. Next, we're going to look at the top of the first hill and the bottom of the first hill, and we're going to draw a line connecting those 2 points, which happen to be at an angle of 45 degrees. We're going to find the length of this using some basic trig, and then we're going to apply Newton's second law on a slant to find the acceleration on the x direction, and we're going to use this in kinematics formulas to find the velocity at the bottom of the hill to be 28.39 meters per second. At the bottom of this hill, we're going to use some circular concepts to find the centripetal acceleration of 27.8 meters per second squared. We're going to find the g-forces, which is 3.84 g's, and we're also going to find the apparent weight, which happens to be 59,488 newtons. And we're also going to find the force factor, which is 1.897 newtons per kilogram. We're going to use the same calculations to find the same quantities when the ride is now at the top of the next loop. So we find that the speed is now 7.65 meters per second. The height of the hill is 41.12 meters. The apparent weight is now 10,550.4 newtons. The force factor is 0.336 newton per kilogram. And the g-forces is 0.336 g's. So using kinematics at the end of the roller coaster, we find the speed to be 33.48 meters per second, and using the law of conservation of energy is 29.4 meters per second. And this discrepancy might be because of the large differences in timings recorded for the students, Miss Burns, and the students of last year. So the kinematics answer might not be as accurate.